Welcome back to the Deep Dive. Today, we are undertaking an architectural thought experiment, one that really every successful tech company has had to face.
That's right.
We're not just going to be defining terms, we're actually building a technical blueprint right here.
Yep.
Our mission is to take the simplest possible idea, a website running on just one single server, and iteratively refine it. We'll go step by critical step until it can seamlessly handle the enormous traffic of millions of users all over the world.
And this isn't just about throwing more hardware at the problem.
No, not at all. It's about making the right and often difficult trade-offs to ensure you get resilience, speed, and, sustainability.
That's right. We're going from, total simplicity, where everything is tangled together,
to a complex, globally available, highly resilient distributed system.
and we need to understand the technical debt that you kind of pick up at every single stage of that journey.
Okay, so let's start at ground zero. The monolithic single server setup.
An absolute beginning.
This is the simplest design you can imagine, and, conceptually, it's actually pretty elegant.
It is.
Everything, the web application logic, the database, any basic in-memory caching, it's all just contained on one physical or virtual box.
And it works. It works perfectly fine when your traffic is minimal.
But we need to understand the path a request takes, even in this trivial setup.
Absolutely.
Yeah.
The request flow is, the foundation of everything that comes next.
Yeah.
When a user types in, say, api.mysite.com,
Right.
the very first thing that happens is an interaction with the domain name system, the DNS.
Which is usually a service you pay for from a third-party registrar.
Exactly. So the DNS takes that human-readable name, and it returns the specific Internet Protocol, or the IP address, of that one single server. Something like 15.125.23.214.
And that IP address is then used by the client, which could be a web browser or a mobile app, to send an HTTP request directly to our one server.
Yep. Hypertext Transfer Protocol.
The server gets it, processes the request, hits its own local database, does its business logic, and then it sends back a response.
And that response is either HTML for a classic website, or, and this is more and more common, it's JSON for API-driven traffic.
And that difference in traffic source is actually really important, isn't it? It kind of dictates what you'll need to do later on.
It's hugely important. A traditional web application handles both the logic and the presentation, so the HTML and JavaScript.
But modern mobile apps, they rely almost exclusively on API calls.
Right. They send these standard HTTP requests, usually using the REST standard, and the server just responds with structured data, purely data, almost always in JSON format.
So an API call like get users 12 hits that single server. The server pulls the data, wraps it in a JSON object, and sends it back.
It's a clean, fast loop.
But what happens when all of a sudden 1,000 users try to do that at the exact same time?
The server hits its limits, and it hits them fast. You start suffering from what's called resource contention.
Meaning everything is fighting for the same resources.
Exactly. If the database is busy doing a heavy transaction, it's starving the web application of CPU cycles.
And if the web app is busy with lots of users, it might use up all the available RAM, which in turn slows down the database queries.
It's this tight coupling. A bottleneck in any single component immediately impacts everything else. The system has basically zero tolerance for sudden growth or heavy load.
Okay, so the moment that resource contention gets bad enough that you notice it, we're forced to make our very first move toward horizontal scaling.
This is the first big step.
The separation of tiers. We move the web application logic onto one or more machines. That's the web tier.
And then the database gets its own dedicated machine, the data tier.
This separation is, it's absolutely crucial, isn't it?
It's a philosophical shift. You're moving from a monolithic structure to a distributed one. And by separating the web tier from the data tier, we enable independent scaling.
So why is that independent scaling so essential? They're both still using CPU and memory, right?
Yes, but their resource needs are fundamentally different. The web tier is typically CPU intensive. It's managing thousands of connections. It's validating inputs, running business logic,
rendering templates, all that stuff.
Right. The data tier, on the other hand, is super dependent on disk I/O and memory. It needs memory for caching indexes and frequently accessed records.
So if we see that our database queries are slowing down because we're running out of I/O throughput, but our web servers still have plenty of CPU,
then you only need to invest in a stronger, dedicated data tier server.
Maybe one with faster SSDs and just a ton more RAM.
Precisely. You focus your spending and your engineering effort only on the component that is currently the bottleneck.
So this early separation, it buys us a lot of time before we have to move to the really complex stuff.
A significant amount of time. It stops you from constantly over-provisioning one giant expensive server when maybe only one specific resource, like disk speed, is actually the problem.
So we now have a dedicated data tier, which is great, but we haven't answered the core question, what kind of database is running on it?
And now we enter the great SQL versus NoSQL debate.
Which is really about defining your system's core priorities, isn't it?
That's exactly what it is. Relational databases, or RDBMS, they're the established standard. MySQL, PostgreSQL, Oracle, they've been refined over decades.
They impose a very strict schema, data in structured tables and rows.
And, most importantly, they guarantee what we call ACD properties: atomicity, consistency, isolation, and durability.
Their superpower is the join operation. That's what lets you build these complex, normalized data models with guaranteed transactional integrity.
For standard business logic, like accounting or inventory management, RDBMS is still, the gold standard.
But the moment you start talking about massive scale and geographic distribution, those rigid guarantees often become, well, prohibitively expensive.
And that's what leads us toward non-relational or NoSQL databases.
This is where the architectural trade-off becomes really explicit.
It does. NoSQL databases, which fall into categories like key value, graph, column, and document stores, they generally sacrifice those relational features.
Specifically complex joins and strict ACD guarantees.
Right, and they do that in favor of better performance and much better distribution capabilities.
And this is probably the perfect moment to bring up a concept that's just fundamental to distributed systems.
Yeah.
The CAP theorem.
Oh, absolutely. When developers are choosing between SQL and NoSQL for a system that needs to scale, they are, whether they knew it or not, choosing their priorities within this theorem.
So break it down for us. What is the CAP theorem?
Okay, so the CAP theorem states that a distributed data store can only guarantee 2 out of 3 desirable properties.
And those 3 are?
Consistency, so all readers see the same data at the same time. Availability, meaning the system always responds, even if some nodes fail.
And the last one?
And partition tolerance. That means the system continues to operate even if communication between nodes fails.
Okay, so C, A, and P, but you only get 2.
And here's the kicker. Since network partitions will happen in any real-world distributed system, you are always forced to choose between consistency and availability.
You have to assume partitions will happen, so P is a given.
Exactly. So if you're building, say, a financial ledger, you prioritize guaranteed instant data integrity. You choose consistency.
Which means you might sacrifice availability during a network outage. Your database might lock up until it can get back in sync.
Right. But if you're building, say, a massive social media feed, you want it to be online 24/7. So you choose availability and partition tolerance.
But you have to sacrifice that instant consistency.
Correct. The relational world tends to lean towards consistency and partition tolerance, or CP. The NoSQL world generally leans toward availability and partition tolerance, AP.
And they accept that data might be what's called eventually consistent across all the different nodes.
And that flexibility, that's what allows NoSQL to distribute data across many, many servers so much more easily.
Okay, so given the power of SQL and decades of it being the standard, why would a scaling application intentionally choose the complexity of eventual consistency and give up the power of joins?
It really comes down to 4 critical requirements that RDBMS structures they struggle with at the extreme end of scale.
Okay, what's the first one?
Super low latency. If you're building an ad tech platform or a real-time gaming leaderboard, response times have to be in the single-digit milliseconds.
And the overhead of relational lookups and index scanning is just too much.
It's often too slow. A simple key value lookup in a NoSQL store is just inherently faster.
And what about the data itself? I mean, not everything fits neatly into those tables we talked about.
That's the second point. Unstructured data. Think about data from IoT sensors, user-generated metadata, or documents that are constantly evolving. They lack a rigid schema.
Trying to force that fluid data into normalized rows and columns is, well, it's painful.
It creates what's called schema-on-write complexity. A NoSQL document store, like MongoDB, allows for schema-on-read, which handles those fluid data models far more gracefully.
And then, obviously, just the sheer volume of data plays a role.
That's number 3, massive data volume. If you need to store petabytes of user profiles, or transaction logs, or media files,
The scaling architecture that's built into many NoSQL systems is just better for that.
it's often superior. They were designed from the ground up to distribute data across hundreds of commodity servers rather than trying to scale one single monolithic relational database.
And finally, there's an efficiency gain when you're dealing with data that's already structured in a format like JSON.
Exactly. If your main job is just receiving and sending JSON data, serializing and deserializing it, a document store can handle that natively and very efficiently.
It avoids that translation overhead you get when you have to shred a JSON object into multiple relational tables and then put it all back together for every single request.
So, yeah. While SQL is the default starting point for most applications, NoSQL becomes a necessity for systems that prioritize massive scale, speed, or flexible data modeling.
Before we move on and start adding more components, we have to formally talk about the two fundamental strategies for making a server handle more load.
Right. Vertical versus horizontal scaling.
And this decision really defines the entire future of the system.
It does. Vertical scaling is the path of least resistance, at least at first. It means scaling up.
You take your existing single server and you just pour more resources into it, more CPU cores, double the RAM, maybe add some high-speed storage.
You make that one server immensely stronger.
And the advantage is simplicity. You don't have to rewrite your code. You don't worry about data synchronization. You're just managing one operating system.
It works well, but only up to a certain point. Successful systems eventually hit these non-negotiable limitations.
First is just the physical hardware limit.
Right. Even the most powerful servers max out. You can buy servers today with 24 terabytes of RAM, but that is still a ceiling.
And the cost curve gets pretty atrocious.
Oh, it's terrible. Doubling performance can sometimes mean quadrupling the cost, especially with expensive enterprise software licenses that are tied to the number of cores.
But the most fatal flaw for a system that's trying to serve millions of users is that single point of failure.
Precisely. If that single, incredibly powerful and incredibly expensive server goes down,
Whether it's a memory failure, a software patch that goes wrong, or just a power supply unit failing,
your entire multi-million-dollar business is completely offline. Vertical scaling just cannot provide the continuous availability that users demand today.
and that inherent risk forces every mature system to eventually choose horizontal scaling.
Horizontal scaling, or scaling out, means adding more servers to your resource pool. Instead of one powerful server, you have 10 or 100 commodity servers.
And you distribute the load across all of them.
Now, this introduces complexity for sure. You now have to worry about network issues, data consistency, how to distribute requests.
But it's the only viable path to massive scale.
It is. Horizontal scaling provides near limitless capacity because you can always just buy and add another cheap server. And crucially, it provides automatic resilience.
If one of your 100 servers fails, 99% of your capacity is still operational.
You trade that operational simplicity for total resilience and the promise of, near unlimited capacity. For any system focused on continuous availability and massive user growth, horizontal scaling is mandatory. It's the foundation.
Okay, so building on that horizontal foundation, our next job is to protect our newly separated web tier and data tier from failure.
We need components that guarantee resilience.
So for our horizontally scaled web tier, we now have multiple servers. Let's say server A, B, and C, all doing the same job.
And this is where the load balancer comes in. The LB is this essential piece of hardware or software that sits in front of them, and it acts as the single public access point.
So the user connects to the load balancer's public IP address.
And the LB then distributes that traffic to the web servers, which are using private IP addresses.
And that separation is a big security enhancement because the web servers themselves are shielded from direct public internet access.
That's the security benefit for sure. But the functional benefit is smart traffic distribution, and really importantly, failover. The LB is constantly monitoring the health of the servers.
So if server A fails its health check,
The LB just stops sending traffic to it.
Yeah.
It immediately redirects all new requests to servers B and C.
Now, for a deep dive audience, let's get into the details here. How does the load balancer decide which server gets the next request? I mean, it can't just be a coin flip.
No, absolutely not. There are different algorithms for different goals, and the choice of algorithm dictates the efficiency of your whole system.
So what's the simplest one?
The simplest is round robin. It just cycles through the servers in sequence, ABC, ABC. It assumes all servers are equally capable, and it handles rapid, short requests pretty well.
But what if one server gets a long, really heavy request? It could get overloaded while the others are just sitting there idle.
And that's the problem with round robin, which leads us to more intelligent options like least connection.
Okay, what's that?
This is usually preferred for longer, more persistent sessions. It directs traffic to the server that currently has the fewest active connections, ensuring a much more balanced workload.
And then there are others, like IP hash.
Right. IP hash uses the incoming request's source IP address to determine which server gets the traffic. This ensures a specific user always goes back to the same server.
Which is useful for stateful applications, though, as we'll get into later, we really try to avoid that in the web tier.
We do. But the key takeaway is that the load balancer is a sophisticated piece of infrastructure, not just a simple switch. The algorithm choice has massive performance implications.
All right, so we've protected the web tier, but our data is still highly vulnerable.
Yes. If that single master database goes down, we're in big trouble.
So we have to introduce replication. We use the standard master-slave relationship to create redundancy.
The master database handles all the right operations, so insert, update, delete, to maintain transactional integrity.
And the slave, or replica databases, handle all the read operations. They just get a copy of the data from the master.
And this architectural choice is based on the 80-20 rule. Most applications are overwhelmingly read-heavy.
So by offloading, say, 80 to 99% of all the read operations to the slaves, we dramatically reduce the load on the supercritical master.
Exactly. It allows the master to focus exclusively on guaranteeing the integrity of the data rights. And we often provision multiple slaves for every one master to handle that distributed read load.
Okay, but this structure immediately brings up that critical challenge in distributed systems again.
Yeah.
Consistency versus performance.
But specifically in replication, we have to distinguish between synchronous and asynchronous replication.
And this is a fundamental trade-off.
It is. In synchronous replication, the master waits for a confirmation from at least one slave that the data has been successfully written.
Before it confirms the write back to the client.
Right. This guarantees very high data integrity. You have a low recovery point objective, or RPO, which means minimal data loss.
But it adds network latency and drastically slows down every single write operation.
Which brings us to asynchronous replication.
What's the difference there?
The master commits the data immediately, tells the client the write was successful, and then it replicates the data to the slaves in the background.
So it's much faster, much better for performance.
Far faster. But it means there's a period of lag, replication lag, where the slave data might be temporarily stale.
And if the master crashes before that data reaches the slave,
that data is lost. You have a higher RPO. Most massive web applications use asynchronous replication because the performance gain is usually worth the marginal risk of slight data loss.
Okay, so we're trading the guarantee of instantaneous consistency for vastly improved throughput and availability. What are the operational implications when something actually fails?
Well, if a slave fails, that's relatively easy. Reads are automatically redirected to the other healthy slaves, or, in a pinch, back to the master. We just replace the failed server.
But if the master fails?
That's a crisis. A slave must be promoted to become the new master.
You mentioned earlier that promoting a new master is complex. Why can't the system just, flip a switch?
Because of that replication lag we just talked about, which is inherent in asynchronous systems.
Ah, right.
If the master fails, the slave that you designate to be the new master might be missing the last few milliseconds of transactions.
So you need some robust way to figure out which slave has the most up-to-date information.
And you need to make sure the old master, if it ever recovers, doesn't mistakenly start writing data again. That situation is known as split brain syndrome.
And that would be catastrophic. You'd have fatal data corruption across your entire system.
It's an operation that is just fraught with risk. This is why engineering teams invest so heavily in disaster recovery scripts and automated failover testing.
All right, we have achieved resilience through redundancy. Now we need to shift our focus purely to speed and efficiency.
We want to reduce the load on our newly resilient database and accelerate data access.
Which brings us to the cache tier.
The cache tier is temporary, ultra-fast storage. It's typically stored in memory using technologies like Memcached or Redis.
And its primary goal is to store the result of expensive database queries or frequently accessed data so the system doesn't have to keep going back to the database for every single request.
Right. By retrieving data from RAM instead of from disk, we're talking about speed gains that are orders of magnitude faster.
From milliseconds down to microseconds.
Exactly. And the benefits just cascade. You get better overall system performance. You drastically reduce the database load.
Which allows the database to focus on fewer, more critical write operations.
And again, the cache tier can be scaled independently of the web and data tiers.
Let's talk about strategy. Our basic example was the read-through cache, where the web server checks the cache first for a hit, or if it's a miss, it queries the database, stores the result, and then returns it. What's another critical strategy for high-volume writing?
The alternative is a write-through or write-back strategy. In a write-through pattern, data is written to both the cache and the database at the same time.
That seems like it simplifies consistency.
It does, but you still have the latency of the slowest operation, which is the database write. In a write-back strategy, data is written only to the cache first, and the write to the database is deferred.
That sounds way faster.
It offers maximum performance, but it significantly increases the risk of data loss if that cache server fails before the data is persisted to the database.
Caching is incredibly powerful, but it's also a bit of a contract with the devil, right?
What?
We're sacrificing the simplicity of guaranteed consistency for speed.
That's a series of trade-offs.
So let's tackle the critical challenges. First up, data volatility.
Caches store data in volatile memory, so they're not designed for persisting important data. If a cache server restarts, all that data is just gone.
You must always be able to recover that data from the durable database.
Always. Next, the expiration policy, or TTL, time to live. It's really easy to get this wrong.
How so?
Well, if the TTL is too short, your cache miss rate goes up, and you're forcing frequent database reloads, which kind of defeats the purpose of the cache.
And if it's too long, your user sees stale data.
Right. The sweet spot depends entirely on how quickly the underlying data actually changes. For data that's shifting constantly, you probably need an active invalidation strategy, not just a TTL.
Which brings us to what's often called the hardest problem in distributed systems: consistency. How do we truly keep the cache and the database in sync?
Perfect consistency in a globally distributed environment is, well, it's practically impossible without severe performance penalties. Often, we rely on active invalidation.
So when a write happens to the master database, that operation triggers an explicit message to remove or update the item in the cache.
Exactly. But because of network latency, there's always a small window where the database has the new data, but the cache still holds the old data. Mastering that race condition is what separates highly scaled systems from unstable ones.
And we also need redundancy in the cache tier itself. A single cache server is a massive single point of failure.
Oh, absolutely.
Yeah.
Caches need to be clustered and distributed, often using a mechanism like consistent hashing to spread the keys across multiple servers.
Yeah.
And you must over-provision your memory,
By how much?
maybe 20 to 30%, to handle sudden spikes in traffic without hitting your memory limits and triggering aggressive eviction policies.
And finally, that eviction policy. What happens when the memory pool is full? We mentioned LRU.
LRU, or least recently used, is the standard. It assumes that data accessed recently is likely to be accessed again, so we discard the item that hasn't been touched in the longest time.
But there are others, like LFU or FIFO.
Right. LFU is least frequently used, good for specific static data, and FIFO is first in, first out. The choice here really reflects the strategic assumption you're making about your user access patterns.
Okay, moving from dynamic data caching to static assets, we introduced the Content Delivery Network, or CDN.
This is an absolute necessity for any system operating at a global scale.
So a CDN is a massive, globally dispersed network of edge servers, and they are dedicated to delivering static content.
Images, videos, CSS files, JavaScript files. It is purely about minimizing the physical distance between the data and the user.
And the benefit is a dramatic reduction in latency. If our main origin server is in North America, a user in Asia faces these long network hops to get an image.
But if we use a CDN, that user gets their images served from an edge server that's maybe in Tokyo or Singapore. It's much, much faster.
Let's trace the flow. A user requests content using a special CDN domain, like https.mysite.cdn.com, sasat.jpg.
If the CDN edge server closest to that user has the file cached, it's served instantly, a huge speed win. If it's a miss, the CDN requests the file from the origin.
And our origin is our web server or maybe some cloud storage.
Right. And the origin, in addition to returning the file, dictates the caching behavior. It includes an HTTP header that defines the time to live, the TTL.
And the CDN just caches that asset for that duration and serves all subsequent requests until the TTL expires.
Which dramatically offloads traffic from our origin servers.
Now, a CDN is a third-party service, so cost and maintenance become key issues.
Right. The cost is tied directly to data transfer volume, which means you need some engineering rigor here. Assets that are rarely requested should probably be removed from the CDN and hosted cheaply somewhere else.
Because the cost of keeping them cached and transferring tiny amounts of data can add up.
Unnecessarily, yeah.
What about the challenge of forcing an update before the TTL expires? Like if we need to swap out a broken video immediately.
That's handled through invalidation. You can use the CDN provider's API to perform a hard invalidation, explicitly telling the edge network to purge the item.
Which is instantaneous, but it's often limited or costly.
It is. A much more common and robust solution is object versioning. You just rename the file or, more commonly, append a new query string parameter, like video.mp4.v3.
So since the URL is entirely new, the CDN treats it as a brand new resource and immediately fetches the correct version from the origin.
Exactly. And we also must account for the CDN itself failing, which does happen.
So you need a CDN fallback mechanism.
It's essential. If the CDN service is down or degraded, the client's configuration has to be intelligent enough to detect that failure and request the resources directly from our origin server.
It might be slower, but at least the site remains available.
Exactly. Availability over performance in a failure scenario.
We've established resilience and speed within a single geography. Now we need to address the final hurdles to achieving true dynamic horizontal scale.
Removing state from the web servers and then expanding globally.
So the difference between a stateful and stateless web architecture is really the linchpin of true scalability.
It absolutely is. In a stateful architecture, the web server remembers the user's session data, their login status, their shopping cart, from one request to the next.
Which then requires what are called sticky sessions on the load balancer, forcing user A's traffic always to go to server 1.
And this makes adding or removing servers a logistical nightmare. If server 1 fails, all of user A's session data is just gone. They're logged out.
And the critical constraint for large-scale systems is you can't easily leverage modern auto-scaling groups, or ASGs.
Right. ASGs let you automatically spin up a new web server when traffic spikes and destroy it when traffic subsides. If the servers are stateful, you risk data loss every time a machine is terminated.
So the stateless architecture mandates that all user state session data, cart contents, user preferences must be externalized.
That state has to live in a shared persistent store, usually something like Redis or memcached or a fast NoSQL database designed for key value lookups.
So the web server now acts only as a pure processing layer. The user presents a token like a cookie or a JWT with their request.
And the web server uses that token to look up the necessary state data in the shared store.
The web servers are now completely interchangeable, disposable units. This unlocks the true potential of the cloud.
It does. It enables horizontal growth without any complexity. You can automatically add 20 web servers in minutes when traffic surges and remove them when the spike passes, saving massive computing costs.
All while guaranteeing that no user session is lost because the state is durable and safe in that shared external storage. When you're scaling to millions, you inevitably cross borders. A single data center just isn't sufficient for either availability or for an acceptable user experience.
Right. You need multiple data centers across different geographies.
This mitigates the risk of regional outages, a flood, a natural disaster, a major backbone network failure.
None of that should take down your entire service. And crucially, it optimizes performance by reducing latency for users who are geographically far away.
So during normal operation, how do we make sure a user in Germany connects to the German data center and a user in Australia connects to the one in Sydney?
We rely on GeoDNS routing. The DNS provider resolves the domain name based on the geographical location of the person making the request.
And this ensures users are directed to the closest operational data center, which minimizes network latency.
Which is essential for user experience.
So what happens when, say, data center 2 in Europe goes offline? How does the GeoDNS system know not to send traffic there anymore?
The DNS provider has to integrate robust health check mechanisms. The system is constantly probing the endpoint services in each data center.
So it's checking if the load balancer is responding, if response times are okay.
Exactly. If the health checks for data center 2 start failing, the GeoDNS provider is instantly notified, and it removes data center 2's IP address from its routing tables.
And then it redirects 100% of that region's traffic to the next closest healthy data center.
It's an immediate, automated traffic redirection that's vital for meeting your service level agreements, your SLAs.
But this geographic distribution creates an incredible data management challenge.
Well, data synchronization. This is the biggest technical headache of all.
You have to replicate data across all data centers. If data center 1 handles US users and data center 2 handles Europe, and DC2 fails.
The U.S. Center must immediately have all the recent European user data ready to serve those redirected users.
And because of the vast physical distance, this replication is usually asynchronous.
Which means you have significant inter-data center network latency, sometimes hundreds of milliseconds. And that latency severely complicates trying to maintain consistency across continents. It forces you to build highly sophisticated conflict resolution mechanisms.
We have a globally distributed, resilient system, but as it grows, the components become more and more complexly interdependent.
We need to introduce mechanisms to loosen those connections, to prevent cascading failures, and to better manage background tasks.
Which brings us to the message queue.
The message queue, or MQ, is a durable buffer, usually stored in memory or on disk, that manages asynchronous communication between different parts of the system.
It fundamentally achieves loose coupling. It separates the service that creates a request from the service that fulfills it.
Right. You have your producers or publishers who send messages to the queue. And then you have your consumers or subscribers who pick them up and perform the defined tasks.
And the core benefit is resilience and decoupling.
Exactly. If the consumer service gets overwhelmed, the message queue simply holds the requests until the consumers can catch up. The producer doesn't have to wait or fail.
So it prevents upstream services from collapsing under the weight of downstream bottlenecks.
Let's use our example of background jobs, like generating a complex report or processing user photos.
Okay.
When a user initiates a time-consuming job, say creating a high-resolution custom-filtered video, the web server is the producer.
It immediately writes a message to the queue that says, process video X for user Y, and then it just returns a success message to the client right away.
Right. And then dedicated video processing workers, the consumers, pull that job off the queue whenever they're ready.
So the scaling benefit is that these two tiers, the web server and the worker pool, are now entirely independent.
Completely. If traffic causes a huge spike in video uploads, the queue just gets longer, but the website itself stays responsive.
We can just monitor the queue length and automatically spin up more processing workers to handle the backlog without ever touching the web tier.
And there are different tools for this. Technologies like Apache Kafka offer highly durable partitioned queues that are optimized for massive real-time streams, while more traditional MQs like RabbitMQ or SQS focus on simpler transactional delivery guarantees.
Now, a quick note on complexity. When you're using queues, the consumers have to be designed to be idempotent, right?
That's a really important advanced operational necessity.
They have to be able to process the same message multiple times without causing side effects.
Because sometimes a queue system guarantees delivery at least once, not exactly once.
So if a consumer crashes right after it picks up a job, but before it confirms it's done,
the queue might reissue that job to another worker. And if that job was, say, transferring money, the system needs built-in checks to make sure that money isn't transferred twice. Idempotency is crucial for financial or any state-altering operations in a queue-driven world.
we've established that managing a distributed system across dozens of servers and multiple data centers is, well, it's humanly impossible without a heavy investment in tools.
These tools move from being a good practice to an essential investment when you get to this level of scale.
Without centralized visibility, you are operating completely blind. When a server goes down, you have no idea why or what triggered it.
Let's start with logging. When you have hundreds of servers, you can't just SSH into each one to read the log files.
No way.
Centralized log management is mandatory. Systems like the ELK, Stack Elasticsearch, Logstash, and Kibana aggregate all the logs from all the servers, regardless of location, into one central repository.
Which allows an engineer to search across the entire architecture instantly to find correlated errors or trace a single user's request as it jumps from the load balancer to the web server to the cache and finally to the database.
Exactly. Now next is metrics. Logs tell us what went wrong. Metrics tell us how the system is performing and whether it's trending toward a failure.
And these have to be layered.
They do. You start with host-level metrics. CPU, memory utilization, disk queue lengths. Then you look at aggregated level metrics. What's the overall latency of the database cluster? What's the cache hit ratio across the entire fleet?
And you monitor these with tools like Prometheus for collection and Grafana for visualization.
And you set up alerts for when key thresholds are breached.
And we can't forget the business context here.
This is critical. You have to monitor key business metrics alongside your technical metrics. Daily active users, retention rates, revenue.
The technical health has to be mapped against business impact.
Right. For example, high latency is acceptable if it only affects 1% of users hitting some expensive corner case. But it's a critical emergency if it impacts 80% of your revenue-generating traffic. This analysis allows you to define and meet your service level objectives, or SLOs.
And finally, automation. All this complexity demands rigorous, automated processes.
Automation is the engine of consistency. We rely on continuous integration, or CI, tools to automatically verify every single line of code that gets checked in.
Through unit tests, integration tests, security tests.
And continuous deployment, CD tools, ensure that the process of building, testing, deploying, and critically rolling back a new version is completely standardized and automated across all data centers simultaneously.
It reduces human error, speeds up deployment, and ensures consistency across the entire globally distributed architecture. We have protected every tier and accelerated the entire system, but we've finally reached the last inevitable bottleneck.
Our core data store is still constrained by the limits of a single master database, even with replication.
We have to scale the data tier itself horizontally.
Even with synchronous replication and offloading all those reads to the slaves, the single master still has to handle every single write operation.
And as the user base grows into the tens or hundreds of millions, that write volume becomes insurmountable for a single physical box.
Even one with 24 terabytes of RAM, it's too expensive, it's too complex to manage, and it still suffers from that inherent single point of failure risk for all of your write operations.
We have to break the master database apart.
The ultimate solution for breaking that database limit is sharding.
Okay, so define sharding for us.
Sharding involves separating a massive database into smaller, independent, manageable chunks called shards.
Every shard has the exact same schema.
But it holds a unique subset of the total data. So instead of one massive table with 500 million users, you now have 5 tables of 100 million users spread across 5 independent servers.
So the application now needs a map to know where the data lives. It needs a mechanism to determine which shard is responsible for which piece of data.
And that mechanism relies on the sharding key, also known as the partition key. It's the column or columns used to distribute the data.
For instance, if we're sharding user data, we might use the user ID.
And apply a hash function, like user to %5. If the result is 3fit, we know that user's data lives on shard 3.
The choice of that sharding key is, it's arguably the most critical and complex decision in this entire scaling journey.
It is a permanent architectural choice.
Yeah.
The key must ensure that data is evenly distributed.
Because if you chose something like country code, and 90% of your users are in the US, then shard 1 would overload immediately while the others just sit empty.
That's known as shard exhaustion or uneven distribution. A good sharding key is usually a unique identifier, ideally one that's randomly generated, to guarantee an even spread of both data and traffic across all the shards.
Sharding introduces a level of complexity that's irreversible. Once you shard, your system is exponentially harder to manage.
It is.
So let's start with the inevitable problem. A shard runs out of capacity, and we need to add a new one. This is resharding data.
And resharding is an operational nightmare. If we move from 5 shards to 6 shards, our hash function changes from per5 to per6, 6.
Which means almost all the data needs to be recalculated and physically moved to a new home.
And that process is time-consuming and risks significant downtime. A common solution to mitigate this disruption is consistent hashing.
Okay, let's unpack consistent hashing because it's a really brilliant solution to a terrible problem.
Instead of a simple modulo operator, consistent hashing maps both the data keys and the servers, or shards, onto a conceptual ring, like a circular hash space.
Okay.
When the key needs to be stored, you move clockwise around that ring until you hit the first server node. That's its home.
So what happens when you add a new server?
If you add a new server, only a small percentage of keys, those that are directly preceding the new node on the ring, need to be moved to the new server. All the other keys stay right where they are.
So it minimizes the data movement during scaling events?
It makes resharding practical, though it's still very complex.
Okay, next challenge. The celebrity problem, or a hotspot key. Even if the data is perfectly distributed, what if one entity, a celebrity, a massive event, a popular product, generates 100 times the traffic of a normal entity?
Then that one shard will be completely overloaded with read requests.
And this creates a critical operational failure. A single busy user can crash an entire shard, impacting thousands of other users whose data just coincidentally lives on that same shard.
The workaround is often manually identifying these hotspot keys and allocating them their own dedicated and maybe even further partitioned set of shards. You have to manage them outside the normal sharding algorithm.
It's a form of manual optimization you have to build into your operational tooling.
It is. And finally, we have to revisit the loss of that foundational relational feature, joins.
Right. Once your data is spread across multiple shards, performing a join operation across those shards is extremely slow or just impossible.
It requires distributed transactions and massive network traffic. The solution is almost always denormalization.
You redundantly store related data in the same shard. For example, storing the user's name on every single post record they create, even though that name is already stored in the user table on a different shard.
You sacrifice storage efficiency for query speed, ensuring that most of your requests can be fulfilled by hitting only one database server.
And with that, we have arrived at the final mature architecture. We've successfully scaled the data tier using sharding for our core relational data, and we've strategically offloaded non-relational, highly accessed data like sessions and profiles to a high-performance NoSQL store.
The system is now composed of specialized, interchangeable, and loosely coupled services. It's protected by redundancy and load balancing, it's accelerated by global caching, and it's monitored by essential tooling.
It's a multi-tiered, globally distributed system that's capable of handling the demands of millions of concurrent users. We began with a single server, and we've ended with a masterpiece of distributed engineering.
It's quite a journey.
And this journey shows that scaling is not linear. It's an iterative process of solving bottlenecks by introducing complexity and then managing the trade-offs that complexity brings.
And that blueprint for success really distills down to these 8 non-negotiable architectural principles for supporting massive scale.
Let's hear them.
1. Keep the web tier entirely stateless. 2. Build redundancy and failover at every single tier. 3. Cache data aggressively and strategically using multiple strategies. 4. Support multiple geographically distant data centers. 5. Host your static assets on a global content delivery network. 6. Scale the data tier horizontally by sharding.
2 more.
7. Split functionalities into loosely coupled services using message queues. And 8. Monitor your system religiously with aggregated metrics and invest heavily in automation and centralized logging.
That roadmap moves you from a concept to a global platform. But even with sharded databases and multi-region resilience, the system is still fundamentally a large set of interacting components. The final evolution of this architecture is taking those functionally separated tiers, like the web server, the payment processing logic, the recommendation engine, and breaking them down even further into tiny autonomous services, often called microservices.
The journey never really ends.
So here's a final provocative thought for you to chew on. If complexity is the price of scale, where in your own life or your own work could you intentionally introduce a small, manageable layer of complexity, a little bit of decoupling to gain massive long-term resilience?
Something to think about.
Something to think about until our next deep dive.